What happens when we disturb an equilibrium? We rock the boat. Everything's settled down, and then we mess it up. Le Chatelier's principle says that when a chemical system at equilibrium is disturbed, the system shifts in a direction that minimizes the disturbance. Okay, so basically we can say that a system at equilibrium fights back when disturbed. Oh, you're going to remove some of my product? Well, I'm going to shift and make more product. Yeah. It's kind of got an attitude. It doesn't want to be changed. It wants things the way they are. We want to maintain equilibrium. So when it gets messed up, the system will shift around to try to restore how things were. Let's go back to our population analogy. So we had this dynamic equilibrium between people living in Narnia and people living in Middle Earth. And people were moving in both directions because people, are never satisfied with where they are. But the rate of immigration in each direction was equal, and so the populations were constant. Now, a spaceship comes and drops a whole bunch of people into Middle Earth. It's suddenly more crowded. What's going to happen to the rate of people leaving Middle Earth? It will increase. Like, it's kind of crowded over here. Let's find somewhere that's got more space. So the rate of leaving Middle Earth increases. As that increases, then the population of Middle Earth goes back down. But the population of Narnia goes up. So we say that the equilibrium has shifted towards Narnia to reduce what happened to Middle Earth. More people were added here that disturbed the equilibrium. Well, let's shift some of them over here and minimize the disturbance. We can't completely remove the disturbance, but we can minimize it. Let's spread it out. What would happen if you took a bunch of people out of Middle Earth? The population would shift back into it. There would be more people moving into Middle Earth to kind of fill up the gap. The population of Narnia would go down a little bit because some of those people would shift over to Middle Earth to make up that change. So if you remove things, the equilibrium shifts to replace them. If you add stuff, the equilibrium shifts to remove it. It's kind of contrary. When we add product to an equilibrium, the rate of the reverse reaction increases. We talked about how the rate of a reaction is affected by concentration. If we have more of these particles, then the rate of reaction going back will be higher. That's the scientific explanation. So the rate of the reverse reaction increases, and the reaction will shift to the left until this slows down. This is actually the forward reaction will gradually speed up as we get more reactant being formed, but eventually they'll settle on a new equilibrium. Okay? The general person how to remember it explanation is, well, if I add a bunch of stuff here, the equilibrium doesn't like that. And so it's going to get rid of some by shifting to the left. And so we'll see that the concentration of reactants increases because I threw in some extra product. Any questions? So here we have an equilibrium illustration. There's 4 of these NO2 particles, and there's 2 of these N2O4 particles. If we throw in more product, we're adding NO2, we throw in 3 more of these. Now there's a higher concentration of these little guys, and so they're going to react faster and create more of those reactant molecules, the N2O4, because they're going to run into each other more frequently. And so we see that the system has shifted to the left. meaning there's more reaction going towards the left than to the right. The concentration of this will increase. There's got to be some questions. Yes?
All right. You lost me there at the end, so I thought that when you increase the concentration of one, you just said it moves to the left, but I thought it moves to the right, making more product.
Well, we're adding product.
Right.
So if we disturb this side, it's going to shift to the other side.
Yeah, it's product or reactant?
I'm adding product. When I add product, it reacts in the reverse, and we actually end up with more reactant in that mixture than we started with. It's easy to misunderstand. There's a lot of words.
Just to the opposite side of where you're adding.
Yeah, it goes to the opposite. If you add stuff, it's going to shift in the other direction.
You mean like it breaks apart into reactants again? Or?
Well, in this case, it's not breaking apart, it's actually combining. But these two that we've added are going to form a new reactant molecule. Because I think one of the things that you first have to grasp is that the reaction can go in both directions. Mm-hmm. In the video we watched, it was the people with the arm on their face, right, and the armless guy. And if they run into each other, they can make two regular people again. So if we add a whole bunch of arm face people to the product, to that mixture, then they're going to bump into some of those armless, missing arm people and make more regular people. And so the number of regular people will actually go up. The number of face arm people is going to be higher too. But the reaction shifts in a way to reduce the number of arm face people compared to what we threw in.
Is that more collisions are occurring?
More collisions. Because if I throw a bunch of these in here, now the collisions between those particles are going to happen more frequently. That causes the reverse reaction to occur at a higher rate. So more of the N2O4 will be formed until the reaction rates become equal again. As these react and the reaction goes in the reverse direction, the concentration of these things goes down and the reaction rate goes down as well. When these react to form more of these and that concentration starts to go up, then the forward reaction rate increases a little bit. And so there's this kind of wiggling. I mean, if you think about standing on a teeter-totter, and somebody puts a block on one side of the teeter-totter, you're standing at the fulcrum right in the middle. You're going to shift the other way to make up for that weight, but there's a little bit of teetering back and forth before you find exactly the right place to stand. It's a little bit like what the equilibrium is that gets disturbed. Does that help? Any other questions? If we add reactant, same reaction here. If we add some of this, then the rate of the forward reaction increases. And so the reaction will shift to the right. We'll see that the amount of product increases, and the amount of reactant at the new equilibrium is less than it was when we first disturbed it. Because we throw some in, and it's going to get rid of some. It's not going to get rid of all of it. The concentrations will not go back to what they were. They can't. But it's going to minimize the disturbance. So here again is that picture. If we add the big molecules here, then the splitting of those into the product, the NO2, is going to be greater. That rate is going to be greater. And so the system shifts to the right. When you add something, the reaction shifts to the opposite side. So summary of this. Increasing the concentration of a reactant causes the reaction to shift towards the products. Adding concentration of products causes it to shift in the direction of the reactants. So these are the sorts of questions we need to be able to ask. here's a reaction. What's the effect of adding more Br2 to the reaction mixture? And your choices are shifts to the right, shifts to the left, no change.
Shifts to the left.
Shifts to the left. If we add this, then the reaction will shift away from that. Oh, you threw more bromine in here? Well, I'm going to go the other way and show you and get rid of some of that. Okay? So for this first one, the reaction will shift to the left. What if we add BrNO? That's over here. It'll shift to the right. What if we remove some bromine? It'll also shift to the right. You took some of that away? Well, I'm going to shift and make more. I'm going to minimize the disturbance that was imposed upon me. Okay, this is kind of one of my philosophies of life. I'm not a fan of change unless it's my idea. I freely admit that. Any questions?